when we're doing these double integrals, problems can arise from two sources. There could be trouble just in the integrand itself. Obviously, in this case, the function we're integrating is very simple, so that's not a problem. But then once you do the integral, then you have to evaluate that antiderivative at the two bounds, and if the bounds are complicated, that can create trouble for you. So it may not actually be that the integrand is difficult. It may be that the bounds make this problem difficult. In that case, there might be a transformation where the bounds of the region would be simpler. We just have to remember to include our Jacobian because that will help us to convert so that we have the correct area. If we look at this region, we're saying that x is between 0 and some number a, and then the y value is between the negative square root of a squared minus x squared and the positive square root of a squared minus x squared. If I look at either of these bounds, let's just look at the right-hand bound. If y is equal to the square root of a squared minus x squared, then y squared is a squared minus x squared, so x squared plus y squared is a squared. That's just a circle of radius a. So these complicated bounds are actually much nicer represented in polar coordinates. Let's see, we're saying x is between 0 and a, and then we have a circle of radius a. Since x can't go negative, really the region we're talking about is this semicircular region. Okay, well, if we change to polar, the description in polar here is that r, that you can face an angle anywhere from here to there, right? So we could set it up with theta between minus pi halves and pi halves, and then facing any of those angles, then the r value is just going to go from 0 out to a. So facing any of these angles, you can start at the pole and walk out as far as you like until you get to a, and then you have to stop. So that is going to be a description of this region in polar coordinates. Now notice that region is just a nice rectangle here. If I look at it in terms of r and theta, theta is just going from minus pi halves to pi halves, and r is just going from 0 out to this value a. So that's a nice rectangular region. The bounds are going to be particularly good here. Now, one thing I have to worry about though is what we're going to be doing this integral. Let's see, from minus pi halves to pi halves in theta and 0 to a in r. So we're going to do some integral dr d theta. When we do that though, a little chunk of area here that's dr by d theta actually represents a different sized chunk in the original region. So what I want to do is to take I want to adjust that, right? I need to adjust that, and we saw that the key to doing that is the Jacobian. We also saw that the Jacobian in this case is r. If you don't remember, just think about the equations that would take you from where you want to do the integral to the region where you want the integral to actually represent that. The equations are x equals r cosine theta and y equals r sine theta. So we set up our first derivative matrix. Dx dr is cosine theta, dx d theta is minus r sine theta, dy dr is sine theta, dy d theta is r cosine theta, and then we take the determinant of that, and we got r cosine squared minus minus r sine squared, so r times cosine squared plus sine squared would just be r. That's always going to be the case. The Jacobian for polar is going to be an extra r. So we have to throw in that extra stretching factor of r. So dr d theta has the wrong size, but if you take a region here, dr d theta, and multiply by r, then that adjusts it so that it has the correct size to represent the size in the original region. So we get to do the integral over this nice region, and we have this to adjust it so that it represents the integral over the more complicated region. If there had been some function of x and y in here, we would have just replaced the x with r cosine theta and the y with r sine theta before doing the integral. Now the integral is going to be easy. You just have to find the antiderivative of r with respect to r, which is 1/2 r squared, and evaluate that between 0 and a. Once I'm done with that, I'll do the integral from minus pi halves to pi halves d theta. So we have integral from minus pi halves to pi halves. If I plug in an r here, I get 1/2 a squared. If I plug in 0, I get 0. So the difference between the two is 1/2 a squared d theta. Of course, 1/2 a squared is constant as far as theta is concerned. It's just the radius of that region. And if you integrate 1 d theta, you're just summing up the length of this interval, and the length of that interval is pi halves minus pi halves, which would be pi halves plus pi halves is pi. So we get 1/2 pi a squared. Well, that should be familiar, right? If we look at this region, we had a half of a circle, and what we were doing was summing up 1 times each bit of area. So we're just basically summing up all the area within the circle. The area of the full circle of radius a is pi a squared, so the radius of half of a circle should be 1/2 pi a squared. Let's do another polar example. Here we have a region in polar. There's nothing too hard about it, so we're just practicing here, because you could do this integral right away, but we might as well have the joy of converting it to a polar region. First, let's look at the region we're talking about. X is going from 0 to 2, and then the y value is, for a given x value between 0 and 2, the y value is climbing from 0 up to the line where y equals x. There's the line y equals x. So we're talking about this triangular region here. Okay, so we need to, if we want to do this in polar, we just need to get a description of this triangular region. So we can see that our angles, our theta angles, are going from 0, right, an angle of 0 to an angle of pi fourths. So we've got nice bounds on theta. Theta goes from 0 to pi fourths, and then we need to get the bound on r. So given a value of theta, you can see that the r can only go until it hits that vertical line. So the r can start at 0, and then we just need to get the equation of this vertical line. So 0 is less than or equal to r. We've got to figure out when does r stop. Well, that vertical line is x equal 2, right? And we want to convert that to polar. Well, x is r cosine theta. So saying x is equal to 2 is saying that r cosine theta is equal to 2, which is saying that r is equal to 2 over cosine theta. Now I have an r as a function of theta. I know how far r can go before we have to stop. R can go until it's equal to 2 over cosine theta. That's when the r is going to hit that line. So we get our new integral now. The theta values are going from 0 to pi fourths, and the r values are going from 0 to 2 cosine theta. Might be, well, 2 over cosine theta. I was going to say it's 2 secant theta. That might be handy in the future. Y, we need to convert that to polar, but remember in polar, y is the same thing as r sine theta. So we have r sine theta. Now we have dy dx, but over here we're going to be doing it dr d theta. And a region here, something in the r theta plane, right, gets stretched by a factor of r. That's the Jacobian here. That's going to give us the correct value. So let's see. We have the integral from 0 to pi fourths. You can see this sine theta, the inside integrals with respect to r, so I might as well pull that sine theta all the way out. And then I can just focus on doing the integral from 0 to 2 over cosine theta of r squared dr d theta. Now our inside integral, antiderivative of r squared is 1/3 r cubed, and we're going to evaluate that between 0 and 2 over cosine theta. And then we're going to integrate that d theta. When we plug that in, we get the integral from 0 to pi fourths of, let's see, r cubed. Up here would be 8 over cosine cubed. So that will be 8/3 then over cosine cubed theta, minus, when you plug in 0 you get 0. So this is what I need to do. Oh, I lost my sine theta. It's right there. Put the sine theta back in. Now with a little simplifying here, sine over cosine is tangent, so we have 8/3. There's one sine over cosine, which is tangent, but there's still 2 cosines left downstairs. So cosine downstairs is secant, though, so this is the integral of tangent theta secant squared theta d theta. Okay, well the derivative of the tangent is the secant squared, and that helps me recognize that this is really the derivative of tangent squared, right? If we had 4/3 tangent squared, when you take the derivative, the 2 would come down, and you'd have 8/3 times the tangent times the derivative of what's inside. Well, the derivative of the tangent is the secant squared, so this is what we need to do. Okay. Now, the tangent at pi fourths is 1, because at pi fourths the sine and cosine are the same, so their ratio is 1. And so if you take 1 squared, you get 1, so we get 4/3 times 1 when we plug in pi fourths. The tangent of 0 is sine over cosine, but the sine of 0 is 0, so that's just 0, so we get our answer here is 4/3. Wow, I think it was actually harder to do this integral by changing to polar than it was to do it originally. Let's just do it as a nice little check on our work here. We're doing the integral with respect to y. The antiderivative of y is 1/2 y squared. Evaluate that between 0 and x, and then integrate with respect to x. So we get the integral from 0 to 2. If we plug in x and 0, we get 1/2 x squared minus 0. So 1/2 x squared dx. And let's see, the antiderivative of 1/2 x squared is 1/6 x cubed. Check my work, take the 3 down. Yeah, you get 1/2 x squared. Good. Between 0 and 2. 2 cubed is 8, so we have 8/6 minus 0/6, which is 8/6, but that reduces to 4/3. So we got the same answer the other way. So nice little example, though, of how we could set up bounds. It's nice because the bounds in polar here are a little more complicated, but we can see we can still do it if we're just careful.